Hi, so this is my second video on lasers. My first one was looking at the Einstein coefficients, and this one's going to be looking at the conditions for a laser. Now, it's worth starting with the meaning of a laser. So you may know that laser is an acronym, and if you're watching these videos, you probably should know at least what they stand for. It stands for the light amplification by stimulated emission of radiation. And it's this word here, amplification, that we're most interested in this video. I just want to mention that I did look briefly at stimulated emission in my last video. I'm also going to be using things from that last video in this video. So if you don't know the Einstein coefficients and you haven't watched that video, you may want to look at that video or look in like a textbook or something else. So we're going to start by looking at a medium, just any random medium, which I'm not going to specify much about except its length, which is going to be called A. We're going to send in a light beam of intensity I0, and we're going to get out an intensity IA. Now, I must say now that this intensity I0 can actually be 0, and in some cases it is, and we still get an intensity IA out. I'm not going to go into detail in that in this video. So for that all-important amplification, we clearly need that IA is bigger than I0. Okay, the condition for a laser. That's it. Video done. Well, not really, because this condition is okay, but we can put it in a different form, which is kind of more useful to us. And to do that, we need to look at the processes which can increase this intensity IA. Oh, not the intensity IA, but yeah. The processes which will increase IA with respect to I0. And I mentioned 3 of these in my last video, and they are the 3 that we are going to be considering. They are absorption, which takes an atom, I will draw this like this, takes an atom from level 1 to level 2 by the absorption of a photon. Now, because this is absorption, it absorbs a photon, it decreases the intensity. It removes the photon and therefore decreases intensity. So this is a bad process. We want less of this for us to have the laser. We then have stimulated emission. Now this puts a photon, an identical photon, into our light beam. So this is a good process. It increases our intensity. And lastly, we have spontaneous emission, which again takes an atom from level 2 to level 1, but it emits a photon in a random direction. And as such, this doesn't really have a large effect on anything. So it's kind of like a null process. I'm going to draw a line to indicate that. It kind of has a good effect, but not a huge one that we need to consider it in much detail. So this process then, or this condition here rather, is equivalent to this condition here, that the stimulated emission is greater than the absorption. And I guess you could also put a plus there, but like I said, we're going to be ignoring the spontaneous emission for the time being. Okay, so okay, this is where we need to put this into a more quantitative form, and it's also where my last video comes in helpful, because we looked at the rates at which these processes occur. Now, stimulated emission occurs at the following rate. Per unit volume is given by N2 times by B21 times by rho omega times by phi omega. I'm going to drop the d omega we had in the last video and assume that this is roughly a Dirac delta function, so that when you integrate over omega, you basically get this. You can also assume we're dealing with specific intensities. Okay, That's the rate of stimulated emission. The rate of absorption is given by this. Okay, and we can do some nice cancelling here. Cancel this with this, and this with this. And we then are going to use a relationship between B12 and B21, which I haven't derived, but which is always true. And that's that B21 is equal to G1 over G2 times by B12. If we sub this into here and divide through by G1 over B12, we get that N2 over G2 must be bigger than N1 over G1. So that is the condition for a laser. Well, it's a sufficient condition. Sorry, no, it's a necessary condition. It's not sufficient because you may have losses and other things going on. This condition has a name. It's called population inversion. My spelling's probably wrong, but this condition here is population inversion, and it can be written in another way. It can be written as N2 minus G2 over G1 times by N1 must be greater than 0. This quantity here on the left hand side is called the population inversion density, and it's given the symbol N star. Okay, so that's the end of this video. We found a condition that we need for the lasers. I guess in my next video we'll be looking at in more detail the rates of changes of processes, or like we'll be looking at steady state conditions and like how this intensity changes, I guess, through the medium. Okay, so thanks for watching. Feedback would be great. Color scheme, I think this one worked better than the last video because you can actually see different colors, but okay.